So this video will walk you through how to do example 1.36 of the linear and quadratic functions booklet. So the first thing is anytime you have a problem that is dealing with questions regarding coordinate geometry, if you can sketch a diagram, sketch a diagram. So therefore, what I've already done is I've already produced a diagram with points A, B, and C being arbitrary vertices of a triangle, where A, 0 and B, 0 is irrelevant as long as they remain on the x-axis, and where 0, C is placed is again irrelevant as long as it stays on the y-axis. So the first thing, we're trying to prove that three altitudes, which hopefully you've read the definition of an altitude above. They're included in the diagram in pink. We're trying to show that the three altitudes are concurrent. So again, if you cannot remember what concurrent is, you may want to pause the video now and look it up. So the first thing I will want to do is I will want to determine what is the gradient of the line that connects A and C. And so y minus y, c, x minus x, negative a. And because the altitude is perpendicular to that perpendicular gradient is going to be opposite sign and reciprocal. And this is going to be the gradient for the altitude that I've labeled line A in pink. All right, so I'm going to do the same thing for the gradient that connects point A to B. That one's fairly easy because we know it's a horizontal line, so therefore that gradient is going to be 0. Perpendicular gradient to that is going to be undefined. And that gradient, that perpendicular gradient, is going to correspond with the line, the pink line that I've labeled, line C. And then again, one more time, I'm going to determine what is the gradient for the line connected, passing through points B and C. And again, y minus y on x minus x. So C on negative B. And again, the perpendicular gradient for the altitude that I've labeled line B. It's going to be opposite sign, reciprocal, B on C. And again, that's the gradient that's going to correspond with line B. And again, remember, we're trying to prove that these three altitudes, so the pink lines, intersect at the same point. So clearly we can see that line C, that's the vertical line, so hopefully you can remember that that equation for a vertical line is x equals 0 because it passes through the x-axis at 0. So then determining the equation for line A, so that's going to be in point gradient form y minus the y value, because it passes through B, 0, equals the gradient of line A is A on C, and x minus the x value of B. Simplifying that is in distributing, and that's our equation for line A. So then line B, again, line B goes through the point A, 0, so y minus 0. Your gradient is B on C, and x minus the x value, which is A. Simplifying that, so B on C times x minus AB on C. So again, remember, we're trying to show where these three lines intersect. So we know that we have an x value. We know that the line C is the x value, x equals 0. So therefore, when x equals 0, by substitution, that line A, when I substitute in 0 for x, I get y being negative a, b on c, or the y-intercept. By substitution again, for line B, again, y equals substituting 0 n for x. The y-intercept for that is also the same thing. So what that tells us is, therefore, the three altitudes are concurrent, intersecting at 0, negative a, b on c is the point of intersection. And we have proven that these three altitudes are therefore concurrent.